Okay. So, good afternoon, everyone. Thanks for coming. Professor Glyn Williams-Jones is a volcanologist from the Simon Fraser University of Barnaby, Canada. He's the co-director of the Center of Natural Hazard Research in the Department of Earth Science. And currently, Professor Glyn is spending a sabbatical year in France at the University of Clermont-Auvergne. So the seminar of today will be about two volcanic centers in Canada, and he will tell us stories of local oral traditions related to the volcanic activity. So, Glyn, thanks. Let's hope we solved all the technical problems.
We have. Great. Well, thank you, everyone. And technology is what it is. So it's great to be here, and I really do appreciate the opportunity to tell you some stories about Canadian volcanoes, and use this a bit as an opportunity for marketing to make the case that in fact Canada does have active volcanoes, and we need your help to better understand those volcanoes. And again, as any of this work that I'm presenting really is thanks to a large team of collaborators, of graduate students who've done the core of this work. So I'm just the poster child who gets to stand up here and present these stories. Obviously, as we all know, Canada, and specifically Western Canada, is on the Pacific Ring of Fire. The volcanoes that you see here, it's going to work, that's showing, that you see here on the slide, all of them have had some level of eruptive activity in the last 2 million years or so. Within the Holocene, so the last 10, 11,000 years, we've had at least 54 eruptions within about 10 volcanically active regions. The dating, I'll say right now, is sparse, so we need a lot more work to better understand and refine this information. Thanks to Natural Resources Canada, which is responsible for volcano monitoring, and I'll get to this later in the talk, our monitoring is quite sparse right now, to say the least, but some foundational work has been recently done identifying 8 target volcanoes of interest that require much further work to better address, both from a monitoring perspective, but also understanding the core fundamentals of those volcanic systems. So today I'll speak to you about 2 volcanic systems, 2 counterpoints. One called Tseax is as you can see here, is in the southern part of what's called the Northern Cordilleran Volcanic Province, and this last erupted in the 1700s. And Kwikwelistan, or Mount Meager volcano, further south in the Cascadia volcanic arc, within specifically the Garibaldi volcanic belt, and that last erupted about 2,400 years ago. So one key thing, especially being here in Italy, Canadian written history is very young, and so in these situations, I think there's a rich resource of information that is still only starting to become recognized in the oral traditions of the peoples that were living in these areas for thousands of years and observing many of these volcanic eruptions. So to start, Kwikwelistan, or Mount Meager, within the Garibaldi volcanic belt, this is a key thing when I'm speaking to the public in Canada. The American volcanoes do not stop at the border. The Cascade volcanic arc continues northwards, and here we can see we're in this subduction zone setting. The volcanism in this area is less frequent than we see in the high Cascades in the central parts of Oregon and Washington, but nevertheless they are active. And specifically, Mount Meager is north of the main sort of population center, Metro Vancouver, and close to the nearest town or village of Pemberton, population about 5,000 people. So small, nevertheless, about 60 kilometers northwest. So Mount Meager has a long-lived volcanic history formed over the last about 2 million years, and the geology is complex. So very much a set of overlapping volcanic systems that have developed over this time period. There is extensive hydrothermal alteration throughout the area. There were this sort of facetious snapshot photo from hot springs at the base of the volcano, has led to widespread geothermal exploration, and some geothermal holes that were drilled reached temperatures well over 220 to 240 degrees Celsius. So interest in terms of geothermal energy production, nothing commercially active at this stage, but this work has been going on for the last 50 years or so. So the other thing that complicates the setting is the Canadian volcanoes have undergone, most of them, extensive glaciations. And so many of the volcanic systems are glacially constrained. And in this case, we've got a large massif that is ice capped. And again, with this hydrothermal alteration, it's going to lead to another part of the story. It's the large instability of the massif. So the work in this area to access and to do the mapping of the geology and the volcanology is challenging. It's, as I said, it's a mere 60 kilometers west of Pemberton, but to get onto the massif, it's essentially helicopter access only, and you're on ice. So you can see in green here these undivided volcanics. That is the extent of our ability to map some of this finer details because of challenges of access and glacier covered. But the really important story here is this system that is consisting of multiple eroded centers, ranging the gambit from basaltic through to rhyodacite. And because of very young geology and high rates of uplift, in fact, it's a wonderful teaching environment because we see the volcanic massif perched up high on the basement. And so from the area just on the southeast, this is called the Upper Lillooet River. That area there's a big river there, obviously, but we can see the contact between the basement rocks, granitic basement rocks, and this perched massif, again leading to some instabilities. What is really important, and I forgot to mention on the previous slide, this area in pink is the most recent explosive volcanic deposits from the 2360 BP eruption. And there's a key area called Keyhole Falls that I'll refer back to shortly. So the most recent explosive eruption happened, as I said, about 2,400 years ago, and went through a phase of essentially explosive eruptions, pyroclastic density currents traveling down. So it's on the south or the eastern flank of the volcano. These pyroclastic density currents travel down into the Upper Lillooet River and have nowhere to go. Simultaneously, there are, and again, the constraints are challenging because of preservation of material, but estimates are an eruption column that reached perhaps 15 to 17 kilometers high. Widespread ashfall, and on the order of about 0.81 cubic kilometer. So again, a nice correlate is of course the proximal eruption of Mount St. Helens in 1980. It's a good comparison. That volcanic ash did travel significant distances, and so there's really excellent work by a colleague of mine at the University of Alberta, Britta Jensen, we identified ash deposits well over 530, 540 kilometers east in towards Calgary in Alberta. So, we're looking at a substantial eruption in a country that has no active volcanoes. Well, of course. So the proximal deposits suggested between 60 to 80 meters of pumice deposits. Again, proximally, some of those pumices are probably over thickened because of slumping during emplacement. But, we had a major event not that long ago in the geological timescale. What becomes really quite interesting is that initial explosive phase transitioned into an effusive phase where we had a viscous core, a dome of rhyodacite form on the flank, dome of flow, very transitional, but that dome eventually failed into a pyroclastic density current, flowed down into that upper Lillooet River on the eastern flank, and as I said, had nowhere to go. That block and ash flow then welded itself because it wasn't able to extend laterally and cool, and ended up forming a dam 110 meters high and about 3 kilometers wide. Completely fragmental material now welded into a coherent wall. The upper Lillooet River was blocked, dammed temporarily. And again, this is key work by my friend and colleague and his team, Kelly Russell at University of British Columbia, trying to piece together this detective story of this event. But estimates are about a half cubic kilometer reservoir formed over a relatively short period of time. We think probably 1 to 2 months. So the eruption is obviously continuing in that period. And this area in the lower left, we see what is called Keyhole Falls. And that small little slot canyon right in the middle of where the waterfall is, that's about 5 meters in diameter. And that formed subsequent to the failure. So over the last 2,400 years or so. So this dam, the reservoir is building up behind it, ends up saturating unconsolidated material sitting upon the welded dam structure, and then that fails catastrophically in essentially a jääkulp, a catastrophic outburst flood. And work by one of Kelly's former postdocs, Graham Andrews, modeling suggested that 2.5 kilometers of that welded dam unzipped potentially in a matter of hours, maybe 8 to 10 hours, which is incredible. But we can see in this lower right area, there are mega blocks of this welded dam material that are radially jointed, suggesting that they were still hot when they were in place 35 to 45 kilometers downstream in the outburst flood avalanche deposits. So this was a very short period of time when we went through this series of quite catastrophic events. Now, where this becomes again interesting is there were peoples in the area when this occurred. And so the traditional territory upon which Mount Meager Coquelicton is located is the Lillooet First Nation. And as I mentioned, Western Canada, Canada in general, is a very young country, but the peoples living in that country pre-colonization had a history of developing and maintaining knowledge transfer through an oral mechanism, an oral tradition. And that oral tradition preserves information that can be used in Western science to try to bring together constraints on our volcanological understanding of these events. And so the Lillooet in their oral tradition, and think of oral traditions as a blend of myths and history, and used in a different structure to what we're used to in sort of the Western context. But this speaks of two medicine men or shaman brothers essentially having a dream sequence speaking about a canoe cutting down through that dam, down the Lillooet River, and then essentially bringing back salmon up to the area that had been dammed In Western Canada, salmon is a fish species. The Pacific salmon is extremely important to the cultures for, fish eating, basically nutrition, but a whole range of other uses. So it's an important tool, and understandable that it would be a sort of a key component of these stories. So there's observations that are preserved that we can start to bring back. The work was done sort of in hindsight, if you like, but I think moving forward, there's a lot of other details, taking that knowledge with the uncertainties like we have in any geoscientific data set, and recognizing where there's opportunities for sort of overlap. But similar stories speak about the instabilities of this massif and repeated major landslide events. And that's another aspect of the story that is very important at Mount Meager in the Canadian context right now. So along with being the location of Canada's most recent large explosive eruption in 2010, it was also the location of Canada's largest ever recorded landslide. So 53 million cubic meters of material failed on the western flank. And again, when I'm doing public outreach, instead of how many million swimming pools are we looking at, rather it's about 20 times the size of the pyramids of Cheops in terms of volume. So a significant volume of rock, here modeled by a former PhD student of ours, Gioacchino Roberti. He did his PhD at University Clermont-Auvergne. So we've got a massif that is volcanically active and is tectonically and geotechnically unstable, and repeats itself. So in 2010, there was again damming of the Upper Lillooet River because of landslide deposits rather than volcanic, and that led to the temporary evacuation of 1,500 people. So currently, right now, this is a major center and major issue for the area. So, as we like to say in English, the elephant in the room, the big question and problem about this massif is it's an active volcano with evidence of slope instability. So that area in yellow, that is the site of the 2010 failure. And work by Gioacchino using satellite radar mapping identified at least 27 slopes with movement on the order of centimeters over, say a 2-3 month period, and with volumes greater than 1 million cubic meters. The volumes are, of course, fairly fuzzy, but the one of particular interest, this area called Plinth Peak, is really of concern because some, we could say, back of the envelope type estimates suggest that if it were to fail coherently, and we're seeing in the July-August periods where there's the greatest amount of melt in the area of permafrost and glacial melt, there's movement on the order of 3 to 4 centimeters over a few months, potentially volumes of the scale of maybe 10 times the 2010 failure, if lots of sequences of events were to occur. So it's a major massif. And again, I forgot to point out, but just northeast of Plinth Peak, if we were to get failure there, is a large hydroelectric facility, a run-of-river facility, with employing operationally at least 4 or 5 people, but about $500 million of investment in that hydroelectric facility. So there's infrastructure and immediate risk from these failures, as well as potential volcanic activity. And the potential volcanic activity really was recognized, and I use the term rediscovered because going retrospectively, people have recognized activity in the area, the smell of hydrogen sulfide, that rotten egg smell. And of course, the indigenous population, the Lillooet Nation, have these stories and traditions speaking to the activity. But through a serendipitous observation, a helicopter pilot who was flying a group of biologists over the area doing a survey for mountain goat population. The serendipity was that the pilot had done an undergraduate degree in geology and had taken a volcanology course and recognized the presence of these glacial-volcanic caves. So this is the Job Glacier, and we can see volcanic gases being emitted. We then, having recognized this in 2016, went into the seismic record to see if there was any other evidence. Admittedly, the seismic network is purely for the tectonic network. It is extremely sparse in the volcanic belt. So there's no proximal seismic sensors. The nearest one is about 100 kilometers away. So if we can detect magnitude 1.5 to 2, we're lucky. So this is really not something that is very useful at the moment. So there's perhaps evidence for a seismic swarm, but we wouldn't, put a lot of evidence into that at the moment. So monitoring is again something I'll come back to, but it's a major gap in the volcanic monitoring, volcanology in Canada at the moment. So the other aspect, recognizing that we had these glacial volcanic caves, here we've had a number of graduate student projects go in using a range of geochemical and geophysical tools, ice radar mapping to get rough estimates of the thickness of the glaciers, suggested 50 to 60 meter thick glacier, shrinking rapidly because of climate change. In fact, in 2021, over a period of 2 months, there was a large heat dome event over Western North America, and we lost 5 meters across the entire glacier overnight, essentially. So it's catastrophic, removal of that glacier and all of the glaciers in the area. But the gases that were being emitted are significant. Just at the mouth of these glacial volcanic caves, the scale here, those are about 50 to 60 meters in diameter and about 40 meters deep to the bedrock. But we're getting well over 200 to 300 parts per million of hydrogen sulfide, lethal levels, of course, 5,000 ppm CO2. Interestingly, sulfur dioxide is being detected. I would have expected that to all be scrubbed away by the hydrothermal system. So the presence of even these low levels suggests that the magmatic system is again very shallow. And fortunately, again, through much work, we're able to work with a team of expert cave search and rescue who went into the ice caves with breathing gear and what have you, and were able to identify the source of this small fumarole. Boiling temperature about 90 degrees Celsius, but beautiful little needles of sulfur, of native sulfur being formed. So clearly the system is active. It's not obviously in an eruptive state right now, but it is certainly not extinct by any means. And again, the challenge of climbing down into an ice cave that is full of lethal levels of gas means that we're not doing regular monitoring of the gas chemistry. It's just too challenging. What we have tried to do in my team is take a forensic approach as well and put other constraints on the magmatic system. So in this case, looking at maybe the silver lining of climate change and these reductions in glacier cover is opening up or exposing some outcrops. In this case, what's called Lillooet Glacier, a small area of subglacial basalts that are now no longer covered in ice and thus accessible. And so one of my current PhD students, Sarah Frere, has been doing some wonderful work sampling olivine crystals in these basalts that are sort of surrounding the more felsic massif to try to put time constraints on magma storage. And her work, which was really meticulous, in this case showed between 1 to 3 months of storage time in a shallow magmatic system prior to this eruption, which we think happened about 7,000 years ago. So that starts to give us some evidence of style of behavior that we could potentially expect in the future at Mount Meager. A follow-on study that she's just hopefully going to be submitting for publication in the next month or so is on another little basaltic system, much older, about 400,000 years old, just to the south of the Massif, called Crack Mountain. And here again, using diffusion chronometry, so the amount of time that elements like iron and magnesium take to diffuse across the crystal boundaries, she's showing transport or entrainment through to eruption on the scale of about a year. So very similar time scales for what we're seeing in that first study. So this, while it's not something we can use definitively from a forecasting perspective, it does help frame the concerns that we have about Mount Meager, in that it is quite probable, like we know about volcanoes around the world, that we could have changes in activity over very, very short periods of time. And to reiterate, we don't have a comprehensive monitoring system at the moment, volcanic monitoring system. So a lot of work still to be done. The embarrassing thing right now, the current setup for monitoring in Canada, there is a nascent developing INSAR satellite monitoring program, mainly targeting 8 volcanic centers. As I've mentioned, our tectonic seismic network is insufficient. So we have one site that I was able to have installed through support from private companies who donated time, helicopter access, instrumentation. And so we have 2 cameras, a small seismometer, and this is a snapshot of the glacier from, I guess this was from last summer. But our monitoring system is entirely insufficient. We are working on expanding that, framing it around the landslide risk, because that is the most prominent issue right now. But we have a huge way to go to even scratch the surface of what Ingevu are doing. So I'll shift a bit to a different style of eruptive activity. This is further north. It's the second youngest eruption in Canada, an effusive event from Tseax. So now we're into, rather than being in a subduction setting, we're now into an extensional regime. So we've got rifting going on, very alkaline rocks, and we're at the southern end of the Northern Cordilleran volcanic province. Statistically, this belt has the highest rate of volcanic activity in the country, with an eruption about every 250 to 270 years. I'll restate, our dating is sparse. These volcanoes are extremely hard to get to, and the scale, the level of remoteness is significant. Tseax is 1,500 kilometers north of Vancouver. So once you're there, access is remarkably easy. And so this work that I'm presenting is largely a work of another former PhD student of mine, Yannick Lemoine. What is important, and again, take these numbers with a grain of salt, but given some of the evidence we have through oral traditions, there's the possibility, I'm very, careful about that, of up to 2,000 fatalities due to this one volcanic eruption, an effusive eruption. But again, as with Mount Meager, there is an issue around location. And in this case, we're looking at a very small monogenetic volcano. And this was one of the questions we needed to address based on some much earlier studies. But because of where the volcano formed, perched up in a little creek, it formed a lava flow that self-channelized and flowed about 30 kilometers northwest to a large river called the Nass River, and emplaced about a half cubic kilometer of basanite, very low viscosity lavas in a sequence of 4 lava flows. So the question we had going into this, based on some meticulous early mapping done in the 1960s, was this one event or 2 events? And what could we say about the emplacement mechanisms in this area? As I mentioned, again, here we have an event recorded in the traditional knowledge and the oral traditions of the Niska First Nation, and that information is incredibly detailed. A much younger event, more observational data, but still challenges faced by colonialism. But thinking about this oral tradition, in the Niska language, it's called a dawak. It speaks of 2 young children who are tormenting salmon. Again, salmon being an extremely important cultural component. And the children are placing sticks into the back of the salmon and lighting them and releasing them into the river, or stones into the back. So the stones end up forming a humpback on that salmon, which is what's called a pink salmon. It has a humpback. The pink salmon spawn in the Tseax and the Nass River in July. So based on that observational information, we have constraints on the time of year when this event occurred, because this was a key component recorded in the oral traditions. So these children are being adolescents, and they're doing bad things. Boys in the back, hint. An elder comes upon these young children and tells them, you must stop doing this. You're going to anger the Creator and be punished accordingly. Unfortunately, teenagers do what teenagers do. They continue. The Creator is angered, and the ground begins to shake. And in panic, villagers living in the area flee across the river. Some are able to make it, but essentially many die in the process. And the story continues of essentially a battle between spirits, this volcano spirit responding to the abuse, and a local spirit protecting the people living in the area. And this feature that we see here, this wooden mask, has this long nose, because the stories speak of this battle and this local protective spirit blowing on the lava flow to cool it and stop it. And as that lava flow interacted with the Nass River, when you go there in person, you see this lava wall that's about 30 meters high, and it is like it is being cut by a knife. And there are beautifully preserved 5-meter diameter lava tubes, radially jointed, that you can just see in this environment. It is absolutely spectacular place. So thanks to these oral traditional constraints, my former student Yannick was able to then bring in detailed mapping and map out 4 distinct lava flows, do the detailed mapping and modeling, and then essentially work out depth, approximate depth to the base of flow. We were not able to see the actual contact with the base. I didn't want to get him doing scuba work in the river, but using some reasonable estimates, he was able to essentially come back to a paleotopography and then enable eventual numerical modeling, which I'll show briefly. But essentially we had 4 distinct lava flows, 2 that are the initial phase, Ropi Pahoihoi in green, in the 2 greens, followed by smaller volumes of A'a flows in the yellow and orange. So really at the last phase. What was, again, interesting as we were speaking with the local community, many people have never even been up to the summit. And that's the summit. It's this innocuous little tephra cone which we're quite comfortable formed after the emplacement of the lava flow. So really, for most non-scientists, they would say, well, hang on, I have my volcano and then I have my lava flows. But of course, if people are more aware, well, we're seeing that the formation after the fact. And so some of the questions we wanted to address in this study were, was it a monogenetic single event, or was it a multi-phase eruptive sequence? Dating, again, was very challenging here, but there had been some sparse suggestions of perhaps a 300 to 400 year interval between eruptive products. And our work showed that, in fact, that wasn't the case. But we wanted to put constraints on style of eruptive activity, scale of the explosiveness, and that work is still ongoing with colleagues. And what could we say perhaps about the magmatic plumbing system? I was extremely fortunate in this project to be working with an incredible scientist who was also a wonderful artist. So his mapping is absolutely spectacular, and we can see some of the work that he's done in terms of mapping out the different flow forms that we see in the lava fields as we go down, ropey pohorhoi, but then inflationary areas and collapse features. And it's just wonderful, wonderful work that led to a really detailed map. You can't see it here for scale, unfortunately, but this was something, it was a product that we presented to the community that hopefully can be used for future hazard management in the area. And while we recognize that it is a monogenic system, of course, that never say never when we're thinking about volcanoes. So to bring in some other constraints, we did fairly meticulous sampling through, again, with permission of the community upon whose territory this event occurred. This is how we work in Canada. It's the traditional territories. We seek permission first because that is the only way to really do this kind of work and the co-creation that is so important. But geochemically, it's probably the most boringly consistent data imaginable but it told a good story. It helped us show, if we look at this trace element data, that in fact it was entirely consistent throughout all of the material that we sampled, both the lava flows and the explosive material, giving us confidence that we were dealing with one singular batch of magma erupting over a short period of time. And then that also enabled some of the numerical modeling. And this was something that was really powerful when we were communicating to the community, because their oral traditions, the community wanted to know, what did their ancestors live through? And we were able to show, in this case, what Yannick did, took the paleo environment, paleotopography, and then input the rheological parameters for the basinite flow and the flux rate of the Nass River, and just started those as the initial parameters and let the models run. Again, this is one flow model using Volc flow developed at Université Clermont-Auvergne, but it suggested in place, so F1 and F2 are areas of where fisheries were being processed, and V1 through 3 are small villages. But we can see in placement of that initial pohorhoi flow, pushing of the river westward across the river valley, destruction of those villages on the order of tens of hours. So it seems very reasonable that we had a catastrophic event for the peoples in this area. And what I haven't mentioned is this area is very, very densely vegetated. The forests are very, very thick. It's not as if someone could flee easily across a plain. Even in the river plain, the vegetation would have been very, very dense and therefore extremely challenging to evacuate if you recognized the event that was in fact occurring. So Yannick was able to put a number of constraints on arrival times. Again, these are modeled. We take it for what they are. And clearly, emplacement slowing down as we got into the lower lower slope area of the floodplain in the Nass River. But nevertheless, something that very high effusion, relatively low velocities, but nevertheless potentially catastrophic. He also took another approach using some of the observational evidence preserved in the oral traditions to put constraints on possible eruption column heights. So using some viewshed analysis by saying if someone in the village who was reporting seeing smoke rising up into the air looking towards the volcano, then given the mountain, the topography in that line of sight, was able to say that it would be entirely reasonable to expect column heights of, between 5 and 10 kilometers. That work is still being refined, given some field work that was done this last summer to further refine and constrain the tephra deposits around the explosive area. Again, very, very challenging given the density of the forests. But Yannick brought all of that information together in a small, what we think of as the most likely sequence of events. So we have this paleotopography. We're up in this area called Crater Creek Valley, perched up on the flank of the mountain. And we then initiate with a fissure eruption. So we have a fissure created probably 300 to 400 meters across, basically filling the width of that small valley, and emplacement of the initial flow, Pohorhor flow, and volumetrically the dominant part of the sequence. Probable fountaining reaching maybe 100 meters within that range. Subsequently, a second Pohorhor flow. We don't have constraints on timing between those events, but more, reasonably, fairly continuous, probably short duration intervals, if any. But we've also got development in the second period of a spatter rampart, and this is well preserved in the environment. Initiation of other centers or coalescence of eruptive centers, small small hornitos forming. So again, small, very localized structures. And then we transition into the last pulse of activity, which are dominated by slightly more viscous, more crystal rich flows and flows. And in this area, again, the one flow barely makes it out of Crater Creek. The last one doesn't. It really just stalls there. But there's big, large, fat plagioclase crystals we only find in those two events. And again, final formation of what became this small monogenetic cone, really at the last gasp of eruptive activity. So, again, this is using a lot of forensic interpretation, what we have to deal with. But in both situations, while we've got these very different styles of activity, I think it points to the fact that in Canada there are a series of active volcanoes, but we also have access to these oral traditions, these resources of knowledge that to date have really barely been recognized for their importance, for the merit to which they can bring our understanding of volcanic systems. And so really it's thanks to those, that knowledge, that we are better able in an environment as challenging as it is. And so a last ask would be, or a statement is that, Canada, we've got young volcanoes. There's an awful lot that needs to be done. And we're looking for help. So people who want to come and see a different part of the world, please, you're very much welcome. So with that, I'll say grazie.
So, okay, thank you, Glyn. There are any questions from home, from remote, or from here? And Francesca?
Thank you very much. Very interesting. So I was wondering, for the first case, since there was this huge landslide in a river, there was any record of a kind of tsunami that was?
Can you repeat the?
Yeah. So the question is, during the landslide at Mount Meager in 2010, the most recent landslide, was there any record of a tsunami? No. There was localized flooding, and in fact, what I didn't mention is there were people in a campsite on the river. It's the Upper Lillooet River, and the debris flow actually went around the campsite, because the campsite was sitting on ancient landslide deposits and was perched above the river. But there was no evidence of even localized sesh wave or tsunami type deposits. The volume, I think, in terms of the river, it was too small for that. In the ancient event, 2360 BP, 2400 years ago, again, downstream, the evidence isn't there. There is really interesting evidence of the formation of the reservoir that was created by the damming of the Upper Lillooet River, and you can see areas of high stand perched alluvial deposits where the river was coming up and we still had material coming down, and then as that failed, we now had these perched features on the edge of the valley. But yeah, there's no evidence downstream. Pleasure.
Yeah.
Antonina.
I have a bit of an insider question. So, because I did my computer. So, I know that there's been a bit of problems getting some of the current history because it's quite linked to how do you determine the property of land, something like that. So for the other volcanoes in the Garibaldi volcanic belt, for example, are there oral stories about previous eruptions that could be exploited by volcanologists, exploited in the best?
Yeah. So it's a question from Antonina regarding oral traditions available either in the Garibaldi belt, and again, a bit of an insider question since Antonina did her PhD in the area. In the Garibaldi belt, I'm not aware at the moment of other oral traditions speaking to past events, but I'm sure they are there. And so part of the exercise of this research, I'm hoping, is to expand the network and make people aware that, yes, we've got volcanoes, and both, the peoples that had been living and continue to live in the area, to build those relationships to help start that sharing process. And Anthony speaks to some of the challenges. In the case of the second volcano that I speak to, Tseax, the very subtle details of that eruption about 300 years ago, different families within the community essentially own rights to parts of those stories. And that ownership, and ownership is not exactly the right term, but it's the best I have in English, but that ownership relates directly to possession of territory. And so you can imagine that with that type of relationship, it is very challenging to expect people to then share all of those details. If I had the exact details, I could lay claim to part of that territory. So that's one of the challenges we face. But more importantly, a challenge is developing the relationships, the trusting relationships, because of the past histories in Canada and North America around colonialism. There are a lot of barriers that still have to be surmounted to build trusting relationships. And in the case with the Niska, that's a relationship now that has been going on for about almost a decade. And we are continuing to strengthen that, but it's a long commitment. But I think it's a very valuable resource, valuable exercise, because there is this rich information. And of course, any observatory, it's the same type of thing. Building relationships with the communities is a core thing that we have to do.
Thank you very much for your speech. I have some questions and some curiosities. First of all, you know that in Italy we have many volcanoes, active volcanoes, and a lot of people that are actually exposed to the risk. How many people live around these volcanoes and are directly or not directly exposed? Directly means, okay, the eruption, not directly the landslides or other. And the second question, you correctly talk about the necessary effort that Canada should carry on to increase the monitoring networks. Who is in charge in Canada? It is, I don't know, an observatory.
Of course, thank you. So the question is, it's a two-part question of what is the population that are exposed to, in the two examples that I covered, to volcanic hazards, and also who is responsible for volcano monitoring in Canada. So the fortunate situation that we have in the two examples that I presented is Canada's population is fairly small in those areas. And if you look at a map of Canada, something like 80 or 90% of our population is within a 200-kilometer distance of the US border. So as we go further north, the population density just disappears. So in the case of Mount Meager, which is 60 kilometers northwest of the village of Pemberton, Pemberton has a population of about 3,000 to 5,000 people. It increases in the summertime during the tourist season to maybe 8,000 or 10,000. But for a proximal eruption, if we were to have another lava flow, really minimal threat in terms of population. There's infrastructure. I mentioned an important hydroelectric facility. Ash dispersal. So one of my former master's students, Rachel Warwick, did some work. And as we get further east, we're starting to look at large population centers, Calgary, for example. So millions of people due to ash, but again, much finer, smaller deposits. So in the proximal area around Mount Meager, very, very limited risk to the population. Tseax, much further north, even smaller. So now we're in populations of hundreds to a few thousand people. So at that level, we're fortunate. Most of our active volcanoes are in remote, rural areas where the population density is very low. It also then adds to the challenge of the monitoring. And so the agency that is responsible for volcano monitoring in Canada is called the Natural Resources Canada. Within that is the Geological Survey of Canada. And there's another associated institute called the Canadian Hazards Information Service. But Canada does not have a volcano observatory. So there are two federal volcanologists. Two. Now you have me on my soapbox. So yes, there are two federal volcanologists, colleagues of mine. Yannick Lemoine, who did his PhD at Tseax, is currently one of those two on a term contract. Hopefully that will change. So we have an enormous challenge ahead of us. The problem in Canada is that we have not had like when I'm in North America, we have not had our Mount St. Helens. We have not had a volcanic eruption in living memory, and thus it is not on politicians' radar. The bigger challenges that we're facing around climate change, slope stability, so massive landslides are ubiquitous in British Columbia. Flooding and wildfires are really catastrophic right now. So in a situation where funding is always limited, that is one of the challenges we face. Again, work by the other federal volcanologist, my colleague Melanie Kelman, is helping change that by doing these threat assessments and recognizing that, okay, we have Mount Meager that is remote, but we have another volcano called Mount Garibaldi further south in the same area. And Mount Garibaldi is close to Whistler and Squamish. These are high tourist areas, many tens of thousands of people, much greater exposure, and are very, very high threat because we do not have good foundational information on these. So a lot of work needs to be done in that space. Her big issue is, of course, like many of us recognize, high threat often entails high magnitude, low frequency. And that is the situation of Canadian volcanism. We've had low frequency in recent recorded history and living memory, but we have the potential for very, very high magnitude events. And so that is an incredible challenge. Very much to be addressed.
Okay. Avete domande? You have questions?
So perhaps in the chat. I'm not sure how to.
Maybe in the chat or no. No. Okay. So if there are no more questions, maybe we can close. Pier Giorgio?
Yes, I stopped the recording. And
Thank you, Pier Giorgio.